Hi everyone, this is Kenneth Wong, Senior Editor for DE 24/7, reporting from Rapid TCT conference at the Los Angeles Convention Center. Here, looks can be deceiving. This banana, for example, is not a real banana but a 3D printed one, showing Stratasys color printing in flexible rubbery materials, and these stretchy pieces are not knitted pieces but 3D printed samples from EOS, showing the fine details possible with high-resolution 3D printing. We saw lots of exhibits that show the expanding variations you can print, from lattice structures in metal and biomechanical models with detailed anatomy to fairy tale landscapes and fantasy characters. We also saw print preparation software with ChatGPT-style UI that understands natural language input, and software that lets you do warp-adjusted modeling or warp-compensated modeling. Don't know what that is? Stay tuned, we'll show you. Usually you print a critical part with a machine, then ship the printed piece to be installed on a car, a plane, or in a factory. But how about a large-scale printing system designed to be transported to the target site?
So think of the heavy industry markets. So think of defense, think of mining, oil and gas, rail, marine. All of those sectors are very, very interesting, and they have the same problem set, is they have large, expensive infrastructure which they need to keep running. And what happens when that infrastructure breaks a $50 part? And it may not be something complex, but it's very crucial to that particular application. So what it means is often that infrastructure is then down. And in a mining site, for instance, that might be costing you $1 million an hour. So at those sites, what they currently do at the moment is they'll either stock a whole bunch of spare parts, which is very expensive, or they'll fly them in. You know, it's not unusual to spend $100,000 to bring in a $50 part. So now think of putting the technology, such as 3D printing, such as advanced manufacturing, at site. And what you're actually then doing is you're able to build that part very quickly. So you're not waiting a week, you might only wait an hour or a day to be able to get that part.
At the booth for 3D systems, we found this new system, EXT 800 Titan pallet. It has an 800 by 600 by 800 millimeter print chamber, so it's pretty sizable. And as the name suggests, this is designed to print not with filaments, but with thermoplastic pellets, usually used in injection molding. It uses nozzles to build objects by extruding the melted pellets. At a glance, the show floor seems to be dominated by hardware, but the real driving force behind design for additive manufacturing might be software.
So I think software is slowly kind of becoming real. It's becoming the critical thing, right? And it's becoming critical due to a number of reasons. For example, if you actually look at the sizes of the machines for the last 3 decades, you'll actually see that the machines are actually like doubling in size or precision every 5-ish years, give or take. And when you see these machines growing in size and growing in complexity, ultimately what you actually start to realize is the machine is great, you know, but it is actually fundamentally limited by the software. Like, we're actually at this unique point in time where the manufacturing hardware has surpassed the software, right? And so if someone is going to make a commitment to buy a large machine or make a major investment in buying lots of these machines, they want to get every nook and cranny of efficiency or potential out of the machine. And the way to do that is, in my opinion, the software. And the software not only unlocks it, but I think it has the opportunity to improve the adoption, because if it's done right, you can essentially democratize a lot of this knowledge that's been kind of kept away or hidden by many actors.
The software plays a key role in all this design for additive manufacturing or additive manufacturing itself, right? The printing process, think about printing process, it takes days sometimes to manufacture a very complex part. Now, how does the engineer knows this is the perfect design for additive manufacturing? How does it know this part is going to perform well? So the tools that we have, the Altair has, help design engineers to design the parts, optimize the parts for particular manufacturing process. In this case, let's say additive manufacturing. I want to know the overhang angles. I want to know if start printing this part layer by layer on SLM, what kind of deformations I will get, what kind of stresses I will get, residual stresses, or if I cut the part off the bed, is it going to deform? It's going to now we can simulate that. We can predict that using a simulation tool. Same with the binder jet. Think about the shrinkage. Think how this part will shrink or deform. We can analyze that. We can predict that, and secondly, we can also compensate the parts for the designers. So,
when you manufacture something in AM, because of the intense heat, the melt pools, and the powder formation process, things invariably get warped or deformed. This is where warp-adjusted modeling or warp-compensated modeling becomes important. Some of the softwares that we have seen let you design things in anticipation of this warping, slightly off-kilter from the intended design. That way, when the printed part actually comes out, it's exactly how you want it.
So we have warp-adjusted modeling, and that works with 3D scanning. So we'll print the part out once, do a whole post-process, get it finished, and then we'll scan it and figure out how warped it is, right? We'll take that scan, we'll put it into the software, GripeCAD print, and we'll actually compare it to the original CAD file, and it'll adjust it on its own. It'll say, okay, it warped this much this way, it's going to counter warp it the other way. It physically changes the STL file and makes a new file that is warped enough so that way when it warps again, when it finishes printing, it warps into the correct geometry.
Usually, warp-adjusted modeling works with scanners because you need to know the degree of warpage to design things to compensate for it. This is where you might use a handheld or tripod-mounted digital scanner to capture the 3D printed object, then convert it into a 3D model for comparison to your original design.
So this scanner here is called the AltaScan Max. And what you're literally doing is scanning the object and putting it into software called HScan, which has all the surface information that allow us now to actually take that cloud or that STL information, in this case take the STL information, to do critical measurements, or we can actually be a little bit more creative and bring that to another software package to understand how much that part may have been deformed. I can actually take the scan data and do quite a few interesting engineering tasks. One of them would be simulation. So in SimuFact, it does a great job bringing in the data, and we can actually simulate the process to see if we have any warpage, and or we can see what kind of defects we have. And a new defect would actually be looking at this process defect analysis. Within that, getting to the layer level down to 50 microns to understand what kind of keyholing we have. If we have a lot of surface information and geometry changes, what's really fascinating is how we can actually take that data from SimuFact and bring in a software like Volume Graphics. And then Volume Graphics, we can actually look at the deformation field and actually create a nice compensated field and send that compensated information back to SimuFact to actually do the simulation process before we actually print out the part, so we can send the compensated mesh to the printer to actually reduce the amount of time and waste it takes to make a good part with the correct geometry and hopefully with no defects. So that's the whole idea behind it. So that's really what it comes down to. The power of Hexagon is be able to utilizing all this different hardware and software tools to quickly get our results. And this time can actually be reduced from literally from months down to literally weeks to days, depending on the type of project we're working on.
So you just really need to point the scanner to the part, and you'll notice I'm just kind of turning this turntable to capture the data. Here we're capturing about 6 frames per second, and based off the geometry and the color content, or we'll talk about texture, it aligns the scans together. And you'll notice on the part there are some reflective targets. Those are not necessary with the Artex scanners, and that's how advanced the systems are, is that they are able to just utilize the geometry of the existing part and the color. And I think one thing else you'll notice is that on this part it is pretty shiny. With the Artex Spider scanners, it is able to capture some of the shiny objects and flat black objects better than most devices. So if I'm done here, I just have to click stop. We can run through the process, which takes a couple minutes to scan. Currently this is just a point cloud, and we're doing a visualization. Once we run through the process, what we actually see is this. So this is just a quick 3D model of the part. If we had this as a scan file, and for instance, we had a CAD file in here, we could come into our software in our measurement and do a quick color map and tell the software, let's go ahead and take a look at both those files and see if they deviate. So what we'll see here is in the green, these are passing, and we can set this color map up in different ways. But right here we can see between the scan data and the CAD data, or scan data to scan data, there's no deviations. But in this little area right here, you'll see in the blue is 0.6 millimeters down, which meaning that during that manufacturing process, we might have lost some material here, as well as on this side. And we could just do a quick color map here and kind of see those areas.
Up to now, most printing workflows involves converting the model into a mesh model constructed out of tiny surfaces or triangles or voxels. It's a reliable method. However, there is a price you pay for that in having to increase the file size dramatically, which in turn demand more computing power in slicing and printing operations. We're now seeing a move towards rethinking the 3D geometry display methods on the computer screens, and specifically, if possible, to reuse the original CAD file, the native CAD file, as the print file.
So Dendrite's vision is to fundamentally change how geometry is created, transformed, and transmitted on a computer. So I see Dendrite as kind of the glue that connects all of these things together, right? When you take a piece of geometry that's been designed, right, you don't want to export it as a mesh or 3MF or whatever. You want to just import the native CAD data, right? You want to bring that in. You then want to transform it, and one example would be like slice it. You want to then send it to the machine, and then in this kind of ecosystem, you want it to be able to interact with the machine, other pieces of software, the powder, right? So I kind of see software sitting at the kind of nexus of it all, and I see Dendrite's vision or goal to kind of connect it all in a harmonious way that democratizes the information that's being sent to each of these parties, and ultimately enables the user to transparently understand how all of these things work in concert with each other.
So this is the build platform. I'm going to add few demo parts on this platform. We'll use some prepared demo files. I have first I will get some mesh parts on the platform, so it looks like that. And now I'm going to get also implicit file, which is designed in Antop with the extension implicits there as well. So we also allow our users to control rendering resolution settings. So here, I will adjust the high resolution slightly higher. It takes just a few seconds, and you see that your implicit file is loaded on the platform, and the high resolution rendering is still being calculated in the background. And once it achieves its high value, the model will be updated automatically. You will be able to see it immediately on the screen. So as I just mentioned, the resolution of the implicit rendering was just achieved right now. You can see the final model here. All right, let's move on. I will add we'll add a label on this part, and this label will be sliced together with the implicits, together with the mesh later in the workflow. So I can hide components, show components, and what is the next step I'm going to show is to get rid of this, it's not needed. I'm going to duplicate my part. I will create multiple copies of it. So I'm going to create multiple copies. For example, 4 copies. You can see that all the components are nicely preserved. They are moving all together and they are perfectly aligned. So I can position them automatically on the platform with our automatic tool, which is called automatic placement. So we'll specify some parameters, and here you can see that my parts are positioned on the platform as I wanted them to be. So I can say that I'm ready to print my parts. So what I'm going to do, I'm going to open the Materialize Inspector software that allows you to inspect your slices, so you can show them all together. You can change the height and check what is the slice file, how the slice on the specific height look like. So I'll just zoom in a bit here, and you will see that the implicits are perfectly sliced here. You also see that, yes, if I go a bit further, you see the labels here as well. They slice together with implicits, and I will go a bit further, higher, and you see that also there is a mesh together with implicit file combined, booleaned together during the slicing process. So that's the workflow. So my slice file is created. I have all the toolpaths generated, and I can just send this file to the build processor without any need to convert my implicit files to mesh.
Just like meshless printing is making things easier, ChatGPT-style UIs are also making print preparation a lot easier.
So if I click the AI stars here, I can say to it, slice my bunny. I remember the name of my design object I imported, and if I press enter, AI is going to try now to connect with our visual programming architecture, and is going to propose different operators to add. So if I add now apply, this will automatically generate the different operators to slice the bunny. And here we are at the center, sliced. That is very useful for people that are starting their additive manufacturing journey, because additive manufacturing, to be very honest, requires highly engineering people to control them, and that's for us a way to really accelerate and help the industry grow through doing very complex toolpath in a very easy way to use. And it doesn't stop there. You can change it as you go. You can say now, change my layer height to 4 millimeters. Now it's thinking again, and being in pink, it means that it's going to update my operator. I can see that it changed to 4 millimeters, so good job, it heard me. And now I'm going to press apply, and it's going to update the layer height to 4 millimeters. And that can go for more operations. It can go up to adding in fields or optimizing for thickness and other elements. It's driving and it's taking information from over 180 operators we develop over 10 years working at AI Build.
During the show, we also found out that the latest release of NTOP, previously called N-Topology, now has a plugin for interoperability with Autodesk Fusion. That is, it lets you import NTOP 3D objects into Autodesk Fusion as native implicit files without converting them into meshes, so we had to see it for ourselves. The blue part here is designed in NTOP, and the new plugin lets you import this part as implicit model directly into Autodesk Fusion without meshing it. Once the file is inside Fusion, you may further use this part as part of a larger assembly, do more structural or thermal simulation tests, then print it on a 3D printer. The word we keep hearing in many booths is AI, the use of artificial intelligence or machine learning to provide in situ monitoring to predict if a part might fail to print or how a part might deform.
But we have the simulation knowledge and the data, so we can use this data and the knowledge to train the AI modules, and user can also do that. They have their existing data from the existing simulation, use that simulation data to train the neural network with our physics AI solutions, so they can predict the failures, manufacturing failures, very quickly in few seconds sometimes. And instead of waiting for simulations, a traditional way of analyzing the simulations, and that's where the AI really comes into picture. Now, stepping back, the Altair, we are reimagining the Altair as a company, as a computational intelligence, which provide the tools for engineers to design or analyze simulations, data analytics, and artificial intelligence. It's basically providing a solution which is innovative to reimagining the world of engineering.
That's a quick roundup of the things we discovered on the show floor at Rapid and TCT conference. For more additive manufacturing and engineering related news, go to DE247. That's digitalengineering247.com. Here are more snapshots from the show floor as I say goodbye. Until next time, I'm Kenneth Wong for DE247.